Wallace teaches chemistry.
Hello everyone, in this video I'm going to be looking at qualitative analysis, specifically how to identify cations and anions. Now, even before we look at our qualitative analysis and the identification of particular ions, we're going to look at what a chemical test is. Now, a chemical test, it works by reacting an unknown material with another chemical. If the substance is present, we see a visible color change, right? If we're testing for that substance and we see that it's a positive result. If the substance is absent, no reaction will occur, and we say that this is a negative result or a negative change. Now, when we're identifying cations, we use two tests. We use the reaction with sodium hydroxide and the reaction with ammonia. We're going to be looking at the reaction with sodium hydroxide first, and usually this is how it goes for cations. So this is our metal cation reacting with the hydroxide ions to give the metal hydroxide, which can sometimes be soluble or insoluble depending on the type of cation that is present. How it works is that for one, we make a solution of the solid in distilled water, and the sodium hydroxide is added dropwise, and we observe the color change or if any precipitate is formed. After that, we add excess sodium hydroxide. So initially we would add about 2 to 3 drops and observe for any precipitate, any color change, and afterwards we add excess sodium hydroxide to see if the precipitate dissolves, if the precipitate is soluble or insoluble. If no precipitate is seen, it is warmed gently to test for the presence of ammonia gas. Alright, so the first test that we're going to look at is the test with sodium hydroxide and calcium cations, Ca2+ cations. This is our Ca2+ cations. We add 3 to 4 drops of sodium hydroxide to the Ca2+, and we notice that a white precipitate is formed. Right, so initially when we added our sodium hydroxide 3 to 4 drops for calcium, we notice a white precipitate is formed. Then when we add excess sodium hydroxide, we realize that that precipitate is insoluble, where it is not dissolved, so we see a little solid floating at the top. This is our reaction, calcium plus hydroxide to give calcium hydroxide. Note the 2+ charge have dropped, hence we put our brackets and 2. Once again, for calcium, when we add 3 to 4 drops of our sodium hydroxide, it looks a white precipitate is formed, and in excess an insoluble white precipitate is seen. So we're seeing a solid. Up next is our aluminum cations. So for aluminum, when we add 3 to 4 drops of sodium hydroxide, we notice a white precipitate is formed. A white precipitate of aluminum hydroxide is formed. When we add excess sodium hydroxide, we notice that the precipitate dissolves. We see that it's soluble and it forms a colorless solution. So for aluminum, in excess sodium hydroxide, the precipitate dissolves, forming a colorless solution. For the reaction, notice it's Al3+ plus hydroxide to give Al bracket OH 3, right? Once again, the 3 drops to the bottoms, brackets 3. Now for the next cation, we're looking at lead. This lead with sodium hydroxide, 3 to 4 drops of sodium hydroxide, forms also a white precipitate, right? A white precipitate of lead hydroxide. Now when we add excess sodium hydroxide, we also realize that this precipitate dissolves, forming a colorless solution. And so we say that the precipitate of lead hydroxide in excess sodium hydroxide is soluble, right? So in excess sodium hydroxide, it would have been a soluble precipitate. The precipitate dissolves, so it would have been soluble, and it looks colorless. Now for copper, when we add sodium hydroxide 3 to 4 drops, we notice that a white precipitate forms at the top, and when we add excess sodium hydroxide, we notice that the entire solution becomes blue, as it is. Okay, so for copper, when we add copper, when we add 3 to 4 drops of sodium hydroxide, we notice that a blue precipitate is formed at the top. When we add excess sodium hydroxide, we notice that this precipitate remains insoluble, right? It does not dissolve, so it remains an insoluble blue precipitate. Once again, the reaction is copper 2+ plus hydroxide to give copper hydroxide, that being our precipitate that we form. For iron 2+, when we add sodium hydroxide to iron 2+, we realize that a green precipitate is seen. When we add excess sodium hydroxide, this precipitate remains insoluble. So we see an insoluble solid. It's a solid that is green. That solid, we call it iron hydroxide. So for the reaction, it is iron 2+ plus OH to give FeOH2. Right, once again for iron, when we add sodium hydroxide to it, it becomes green. A green precipitate is formed. And when we add excess sodium hydroxide, we realize that that precipitate is insoluble. Up next, we have iron 3+. For iron 3+, once again, when we add the sodium hydroxide, a red-brown precipitate is seen. In excess sodium hydroxide, the precipitate is still red-brown and it remains insoluble. Alright, so an insoluble red precipitate would be seen when we add excess sodium hydroxide. For the reaction, it is Fe3+ plus OH minus to give FeOH3. This reaction, up next we have ammonia. Now, if we notice that there is no change at all, we form no precipitate, then we can test for ammonia ions using heat. And when we add heat to this test tube, we're going to realize that a gas comes off. This gas is usually a colorless gas that is pungent. So it's a pungent, colorless gas of ammonia that comes off. Right? Now the reaction is NH plus OH to give ammonia, gas, and water. Now if we add excess sodium hydroxide, no precipitate still forms. Another test that we can use for ammonia, we're going to get into this for our anions and the test for gases as well. But another change is that since ammonia is somewhat basic, we can use a litmus paper. And when we use a litmus paper, we realize that it will change to blue to suggest that a base is present. Now once again for ammonia, if ammonia is present, if we're testing for a particular cation and ammonia is present, we would notice that there is no change, no precipitate is seen. Then we warm it and we realize that a gas comes off, a colorless gas comes off, which has a pungent smell, and so we see that ammonia gas is present. Also in excess, no precipitate is formed. And along with this, we could also use a litmus paper test, which would change blue to suggest that the ammonia is present. In other words, the ammonia gas is present, which is a base. Last test for the cation would be zinc, and Zn2 plus zinc with sodium hydroxide 3 to 4 drops. This would give us a white precipitate, and in excess sodium hydroxide we get a soluble colorless solution. Right? For the reaction, it is Zn2 plus OH minus to give ZnOH2. That's the reaction. Okay, now let us summarize to see what we have learned. So it says for all cations are white in sodium hydroxide, right? Except iron 2+, which is green. The iron 2+ hydroxide is a green precipitate. Copper 2+ hydroxide is a blue precipitate, and iron 3+ hydroxide is a red-brown precipitate. So all of them form a white precipitate except iron 2+, which is green. That's for the hydroxide. Copper 2+, which is a blue precipitate for the copper hydroxide, and iron 3+, when it's in the hydroxide form, it has a red-brown precipitate. Note that ammonia also doesn't form any precipitate at all. Said we see ammonia gas. Right, that's for our ammonium ions, if the ammonium ions are present. Alright. Now another point to note, another summary is that in excess all form insoluble precipitate. In excess, they all form insoluble precipitate, except, I'm going to use a little thing to remember it, except ZAP. So in excess, they all form insoluble precipitate except zinc, lead, and aluminum. Alright, or we can say zinc, aluminum, and lead. So all form insoluble precipitate in excess except zinc, aluminum, and lead, which you would not see any precipitate. It would be soluble, hence a colorless solution will be seen. Right? Another point is that if ammonium cations are present and it is heated, no precipitate forms. Instead, we see a colorless pungent, well, we wouldn't see the colorless gas, but a colorless gas comes off, which is pungent, and this colorless gas is NH3 gas. Now, a question says, what is the color of the calcium hydroxide? Remember, calcium hydroxide would be a white precipitate, and For calcium hydroxide, it is also insoluble. Remember that all would form insoluble precipitate in excess sodium hydroxide except zinc, aluminum, and lead. So we can say that initially calcium hydroxide would have been a white solid, right, a white precipitate, but it remains insoluble. It continues to remain insoluble if we add excess sodium hydroxide to it. Number 2 says, which 3 cations give soluble hydroxides in excess sodium hydroxide? Zinc, aluminum, and lead. Those 3. Number 3 says, color of copper hydroxide. That's right, there is blue, and copper hydroxide, it's blue. And also in excess sodium hydroxide, we will still remain to see a blue insoluble precipitate. This also says what's the color of FeOH2. Know that this 2 here is telling us that Fe would have a 2+ charge. So we say that iron 2+ is green. If it were iron 3+, we know that that would have been a red-brown, right? That's for the recap for sodium hydroxide. Now we're going to look at how these cations react in ammonia. So the first one is calcium Ca2+. When we add 3 to 4 drops of ammonium hydroxide, no change. We see no change. No change occurs when we add 3 to 4 drops of ammonium hydroxide. Even in excess, no change is also seen. So the calcium doesn't react with the ammonium hydroxide. Up next is aluminum reacting with the ammonium hydroxide. This forms a white precipitate, and for this, when we add excess ammonium hydroxide, we notice that an insoluble white precipitate is seen. So it remains white even when we add excess, and it is insoluble. Once again, the reaction is Al3+ plus the hydroxide ions to give aluminum hydroxide. Up next is our lead. Lead would form white precipitate with ammonium hydroxide, and also in excess it remains insoluble. In excess ammonium hydroxide, the lead hydroxide will remain insoluble. It does not dissolve, so we still remain to see a white precipitate. For zinc 2+ ions, we also see a white precipitate when we add 3 to 4 drops of ammonium hydroxide. However, when we add excess ammonium hydroxide, it becomes colorless. So we say that the zinc hydroxide would be soluble, right? It becomes a colorless solution, you see. For the reactions, it would have been lead hydroxide, lead plus the hydroxide ions to give lead hydroxide, and zinc plus the hydroxide ions to give zinc hydroxide. When it's coupled with ammonium hydroxide, we see the blue precipitate, yes, but in excess ammonium hydroxide, that precipitate is soluble, so the entire solution becomes blue, right? Once again, the reaction is copper 2+ plus hydroxide to give copper hydroxide. If it were iron 2+ is green, that would be a green precipitate that is formed when it reacts with ammonium hydroxide. In excess ammonium hydroxide, it remains insoluble, right? So it does not dissolve, it remains insoluble. We still remain, or we still continue to see the insoluble green precipitate. For iron 3+, the initial color change, the precipitate that we see is going to be a red-brown precipitate with ammonium hydroxide. Right here, red-brown precipitate with ammonium hydroxide. In excess, this precipitate is insoluble. Notice for the reactions, iron 2+ plus hydroxide to give iron hydroxide, and iron 3+ plus hydroxide to give iron 3 hydroxide. Okay, let us do the summary for the ammonium hydroxide. So it says, in ammonium hydroxide, calcium does not form precipitate. That's something that we know. In ammonium hydroxide, they all form white precipitates except copper 2+, which would give us a blue precipitate, right? And remember that with excess, that blue precipitate is soluble, so the entire solution is going to be blue. For iron 2+ is green, and in excess it would be insoluble, right? Iron 3+ is red-brown, and in excess it's also insoluble, right? Continuing, in excess ammonia, all are insoluble. Listen, in excess ammonia hydroxide, or in excess ammonium hydroxide, all are insoluble except Zn, and Cu2+. In excess ammonium hydroxide, all are insoluble except Zn and Cu2+, which are soluble, right? That's why for this you would have seen a blue solution in excess ammonium hydroxide, and for zinc, we would have seen a colorless solution in excess ammonium hydroxide. Now these questions says, does calcium 2+ form precipitate with aqueous ammonia, also known as ammonium hydroxide? The answer would be no, we don't form any precipitate if we add 3 to 4 drops or even in excess ammonium hydroxide. Number 2, what color precipitate does Zn form with ammonium hydroxide? The color for Zn in ammonium hydroxide is going to be white. Note that most form white precipitates except copper, iron 2+, and Fe3+. So zinc is going to form a white precipitate, and in excess that white precipitate is soluble, so we would see a colorless solution in excess. Right? Number 3, what cations dissolve in excess aqueous ammonia? So what cations dissolve in excess aqueous ammonia? This is asking us which cations are soluble in excess aqueous ammonia. The ones that are soluble, remember the rule, all cations are insoluble in ammonium hydroxide except those of zinc and copper, and this is for the excess, right? So the correct answer would be zinc and copper. Right. Now notice that for aluminum and lead, they both have the same changes irregardless of the type of solution they're placed with, or regardless of the type of test that we use for them. So remember that for sodium hydroxide, aluminum forms a white precipitate. Both lead and aluminum forms white precipitate, and they're both soluble in excess sodium hydroxide. For aluminum and lead with ammonium hydroxide, they both form white precipitate and are both insoluble in excess ammonium hydroxide. So how do we identify whether lead is present or whether aluminum is present? And the test that we're going to use is potassium iodide. Now when we add some drops of potassium iodide to aluminum, no precipitate is seen. Remember that when it would have been in excess ammonium hydroxide or in excess sodium hydroxide, we would have seen a particular color, right? It would have been soluble in sodium hydroxide, excess sodium hydroxide, and insoluble in excess ammonium hydroxide. But when we add the potassium iodide solution to it, no precipitate is seen or no color change is seen. But for lead now, when we add our potassium iodide to the lead hydroxide, we notice that a yellow insoluble precipitate is seen. So we're going to form some lead precipitate, and it falls to the bottom of the test tube. Just remember that aluminum and lead, they aren't the easiest to identify, so we have to do another test besides sodium hydroxide and ammonium hydroxide, because they both give the same positive test in both solutions. Hence, we use potassium iodide, which gives a yellow insoluble precipitate, right, of lead iodide. So this is what we're going to form, and no precipitate is formed when we use aluminum with potassium iodide. Now we're going to look at the identification of anions, and for anions several tests can be done. First, we can heat the solid in a dry test tube. That's the first test that we can do, and we can test for the gas that is evolved. We can also react our solids with dilute nitric acid or concentrated sulfuric acid. We can also react these solids with silver nitrate followed by ammonium hydroxide, and also we can react them with barium nitrate and followed by dilute acid. The first one that we're going to look at is when we heat the solid. When we heat the solid and a particular gas evolves. Now notice for this test it says heat the solid in a dry test tube and we test the gas that evolves. First one is carbonate, which is CO₃²-. Now for carbonate, whether it could be sodium hydrogen carbonate, which we call sodium bicarbonate, or sodium carbonate or calcium carbonate, etc. Right? When we have our carbonates and we heat the solid, we're going to evolve some carbon dioxide gas. Note that I would have stopped my test tube to prevent the gas from escaping, and it's going to flow through a small tube. Right? Now this gas flows through the tube and it comes out in calcium hydroxide. Now for carbon dioxide, if carbon dioxide gas is present, it's going to give a positive test where carbon dioxide in calcium hydroxide, we're going to see a white precipitate. Calcium hydroxide, another name for calcium hydroxide is what we call slaked lime. Once again, if a carbonate is present, any carbonate, and we heat that carbonate, carbon dioxide gas is evolved, which when we add it or when we place the carbon dioxide gas in calcium hydroxide, also called slaked lime, a white precipitate is seen. Now this is our reaction. Carbonate, we heat the carbonate to form oxygen gas and carbon dioxide gas. Right? Now the next test is to test to see if nitrate anions are present. Now we heat our nitrate anion solid and oxygen gas is evolved. Right? Now the nitrate ions can either be potassium nitrate or sodium nitrate. It's very specific. It can either be potassium or sodium nitrate because these are the most reactive ones. Once again, if it's a nitrate present with a nitrate of potassium or sodium, oxygen gas is evolved. And as we know, for oxygen gas, if oxygen gas is present, the glowing splint will relight, right? So the glowing splint will relight if oxygen gas is present. This is the reaction 2NO3 to give 2NO2 plus oxygen gas, right? So the glowing splint will relight to give us our oxygen gas. Now for metals, if for example we have our anion and that anion is attached to a metal lower than calcium or is calcium and lower than calcium, then we're going to evolve two different gases. We're going to evolve our nitrogen dioxide gas and our oxygen gas. Now if nitrogen dioxide gas is evolved, a brown, we're going to see like a brown gas coming off. That's the color of nitrogen dioxide, it is brown. And if oxygen gas is evolved, it will relight the glowing splint. Once again, for nitrates that are attached to cations, which could be calcium or lower than calcium in their metal reactivity series, it will produce nitrogen dioxide gas and oxygen gas. To test for the presence of nitrogen dioxide gas, you would simply see a brown gas coming off, and for oxygen gas, it would relight the glowing splint, right? Just to summarize, carbonate, when we are testing for the presence of carbonate anions, it will evolve carbon dioxide gas, which will form a white precipitate in calcium hydroxide solution. If we're testing for the presence of nitrate anions, right, if it's the most reactive metals, then only oxygen gas is evolved, and we can test for the presence of oxygen gas using a glowing splint which will relight. If it's metals that are, if the nitrate anion is attached to calcium or metals lower than calcium in the reactivity series, then oxygen gas is evolved and also nitrogen dioxide gas is evolved. The nitrogen dioxide gas would be a brown gas and the oxygen gas would be colorless, but to test for the presence of oxygen gas, it would relight a glowing splint. Up next, we're looking at the reaction with dilute acid, and for this one we're only doing two tests, test for carbonate and the test for our SO₃² anions. Now what we do is that we add either dilute hydrochloric acid or dilute nitric acid to a spatula of the solid in a test tube. It is heated if necessary until a gas is evolved. Once again, for carbonate, if carbonate is present, carbon dioxide gas is evolved. Note that for this test, we have our solid and we put dilute hydrochloric acid or nitric acid onto that solid, right? It will evolve carbon dioxide gas, which, as we know it, for carbon dioxide gas, to test for the presence of that gas, we can place it in some calcium hydroxide solution, which will form a white precipitate if carbon dioxide gas is present. For the reaction, is carbonate plus the H plus ions from the acid. Remember that our acids give H plus ions, right? So it's carbonate plus the H plus cations or the H plus ions to give carbon dioxide and water. That would be what is formed. Now if we're testing for SO₃²-, the gas that is evolved is SO2 gas. Right? That's the gas that is evolved. So for SO3, we put our solid in the test tube, and for this test specifically, we add right. Now for this test, SO₃²-, we would have added our dilute acid. So we add our dilute acid, HCl or HNO3. When we add our HCl or HNO3, it produces SO2 gas. Remember, that's the gas that will be dissolved. So when we add our acid to our SO₃²-, it produces SO2 gas, sulfur dioxide gas. Now this sulfur dioxide gas, to test for the presence of sulfur dioxide gas, we add potassium permanganate, which is purple. If sulfur dioxide gas is present, the potassium permanganate will change from purple to colorless. Let me go again. Right? So we have our solid, our SO₃² solid, which we then add dilute nitric acid or dilute hydrochloric acid. When we add our acid, SO2 gas is evolved. Right? Sulfur dioxide gas is evolved. This sulfur dioxide gas, to test for the presence of the sulfur dioxide gas, we can further add potassium permanganate, which is purple. If the potassium permanganate changes from purple to colorless, we say that sulfur dioxide gas is present, or that gas will be evolved. Now for the next test that we're going to look at the reaction with sulfuric acid, which is our concentrated sulfuric acid. So what happens is that we have our solid, and a few drops of the sulfuric acid is added to that solid. The gas that is evolved is tested. And I hope you remember that if it were carbonate anions present, right, we add our sulfuric acid to it, the gas evolved is carbon dioxide. To test the presence of this carbon dioxide, we simply add some lime water, and that lime water will turn white, so we see a white precipitate. If the SO₃² anion is present and we add our sulfuric acid to it, then SO2 gas is going to evolve. The SO2 gas, we won't be able to see that SO2 gas, but if we were to add purple potassium permanganate, that purple potassium permanganate will change to colorless, to suggest that SO2 gas is present. If HCl gas is present, right, what we would do is that we would react it with some ammonia. So once again, what happens for these tests is that we have our solid first, and we add sulfuric acid to that solid, right? So the solid would have contained Cl- anions. Once we would have added the sulfuric acid to this, then it produces hydrogen chloride gas. Right, so that's what happens when we add the acid to the chlorine or the chloride ions. It's going to produce hydrogen chloride. Right, now for this hydrogen chloride, it reacts with ammonia gas to form a white gas of ammonium chloride. So if chlorine anions is present and it's further reacted with ammonia gas, a white gas is seen. And you would have seen something similar when you did the diffusion in the first part of the syllabus, right, where you have hydrogen chloride gas reacting with ammonia gas to form a white gas, right? You can skip back the book to try and find those notes. It's a good revision. Then we also have bromine or bromide anions. If bromide anions are present and it reacts with the sulfuric acid, it's going to release bromine gas, and that bromine gas is red-brown. Also, if iodine anions are present, usually the solid is gray-black. So iodine anions is present, the solid is gray-black. When sulfuric acid is added to these iodine anions in the solid, right, it will begin to produce a gas per se, especially if it is heated. Right? I remember that iodine is a substance that is able to sublime, so it's going to sublime from the solid to the purple gaseous vapor of iodine gas. So for the next reaction, we're looking at the reaction with silver nitrate followed by ammonium hydroxide. So first we add some So first we add some nitric acid to the solid, and then we add a few drops of the silver nitrate solution and observe the color of that precipitate. After which we add aqueous ammonia and look to see if the precipitate dissolve. Alright, so the first one we're going to look at is the chlorine. So first we're adding our silver nitrate to the chlorine, right? And if you think about the reaction, if you add silver nitrate to something that has chlorine ions, then you're going to have double displacement happening and we form silver chloride. Silver chloride is a white solid, right? So if chlorine anions are present, or chloride anions are present, then we would see a white precipitate form on the reaction with silver nitrate. Note that this white precipitate becomes purplish grayish in the presence of sunlight. Alright? Now when we add some ammonium hydroxide to this solution, we realize that the precipitate dissolves, forming a colorless solution which is soluble. Right? So the ammonium hydroxide would form, when we add the ammonium hydroxide, we create a soluble precipitate, the precipitate dissolves and so the solution would be colorless. So we say that that precipitate is soluble. If bromide anions are present and we add silver nitrate, then we see a cream precipitate, right? So it's silver plus bromine anions to give silver bromide, which is a cream precipitate. Once sunlight touches it, we see a slightly green color coming on. Alright, that's for bromine anions or bromide anions. When we add some ammonium hydroxide or aqueous ammonia, same thing, right? We realize that the precipitate is slightly soluble. So it's gonna look somewhat pale cream, like a palish cream color. That's what we see. If iodine or iodide anions are present and we add silver nitrate, it changes to yellow for the iodide anions. So Ag plus I minus to give silver iodide, which is a yellow precipitate. If we further add ammonium hydroxide, we realize that this precipitate remains insoluble, it does not further dissolve. So what we can conclude is that when we go down group 7, so it's chlorine, bromine, iodine, when we go down group 7, the anions become more insoluble. They become more insoluble. Notice they're becoming more insoluble. So it moves from soluble to slightly soluble to insoluble. They become more insoluble in the presence of ammonium hydroxide. Another thing is that the color change of the chloride or of the silver chloride, silver bromide and silver iodide is that silver chloride is white, silver iodide is cream, silver chloride is white, silver bromide is cream, and silver iodide is yellow. Right? So once you can remember this, and you're good to go. Once again, if we add nitrates to our group 7 anions, the chlorine, we're going to form silver chloride, which is white, then silver bromide, which is cream, a cream precipitate, and silver iodide, which is a yellow precipitate. On addition of our ammonium hydroxide, we realize that it moves from soluble for silver chloride to slightly soluble for silver bromide and insoluble for silver iodide. This test is a reaction with barium nitrate followed by dilute nitric acid or dilute hydrochloric acid along with heat. So for this test, we're really testing to identify the sulfate anion. So the first thing that we do is that we're going to make the solid into a solution, right, using distilled water. Note that for the previous test that involves solids as well, we would have placed them in distilled water just because you know that there wouldn't be any form of displacement reaction if it's just a solid present. It has to be either molten or it has to be dissolved in water so that the ions can be released and then we can further see a reaction. Alright, so for this one, once again, we're doing we make a solution of the solid in distilled water. Number 2, we add some drops of barium nitrate or barium chloride to that solution, and this is followed by a test with dilute nitric acid or hydrochloric acid along with heat. Now, the first one we're going to look at is the reaction of the carbonate anions, any one of the solids. So we add our barium nitrate or carbonate anions, we see a white precipitate. This white precipitate, notice that we're adding barium nitrate to carbonate, so it's a displacement reaction. We're going to form barium carbonate, which is the white precipitate. If we do a next test, which is that we add nitric acid to our previous barium carbonate, right? Note that it's barium carbonate, so we're going to release some carbon dioxide gaseous molecules. So that's what's going to release. We're going to release carbon dioxide gas, and the precipitate of the barium carbonate would have been dissolved, right? So it would be soluble. Once again, we release carbon dioxide gas, and if you remember, to test for carbon dioxide gas, we would use calcium hydroxide, which you would see a white precipitate being formed, right? So once again here, as you can see for the reaction, we have our carbonate with, this is the hydrogen ions coming from the acid to form carbon dioxide plus water. If it were the sulfate anions present in the solid and we add barium nitrate, we also see a white precipitate forming, right? So look at it again, barium nitrate plus the sulfate, we're going to form plus the sulfite, it's going to be barium sulfite, right? And this is a white solid. Now when we further add nitric acid to our barium sulfite, so we add our nitric acid to the barium sulfite, it's going to release SO2 gas. So we're going to release some SO2 gas, as we can see here. The precipitate also dissolves, so we see that the precipitate of barium sulfite is soluble, it dissolves, and when we add the heat, we see our SO2 gas. This SO2 gas, I'm not sure if you remember, but for SO2 gas, to test for the presence of SO2 gas, we use potassium permanganate, which if sodium dioxide is present, right, which is SO2, if it is present, the potassium permanganate changes from purple to colorless. For the reaction, this is it. We have our sulfite reacting with the hydrogen ion from the acid to give us SO2 plus water. For the last reaction, so this is the sulfate cation. If that is present in any solid, we also see a white precipitate form. So that white precipitate will be barium sulfide. Once again, we're adding barium nitrate. It's a displacement reaction, so we see barium sulfide, which is also a white precipitate. Now for this one, no reaction occurs, right? So if it reacts, if the barium sulfate were to react with some dilute nitric acid or dilute hydrochloric acid, we would see no reaction, no gas would be evolved. So let's do a quick summary. To summarize, we say that barium carbonate, barium sulfite, and barium sulfate are white solids. They form white precipitate in barium nitrate. Now, if we were to add some dilute acid, whether dilute hydrochloric acid or dilute nitric acid, to either barium carbonate, barium sulfite, or barium sulfate, we realize that for barium carbonate, we release carbon dioxide gas, which we can test for the presence of that carbon dioxide gas using calcium hydroxide, which changes to a white precipitate. If we have barium sulfite, it releases sulfur dioxide gas, and to test for the presence of sulfur dioxide gas, we use potassium permanganate. Potassium permanganate will change from purple to colorless. The next test is barium sulfate, right? Barium sulfate, we know that it's a white solid as well, but it does not react with dilute nitric acid or dilute hydrochloric acid. Okay, so let's look at identifying gases. The first one we're going to look at is oxygen gas. When we're identifying oxygen gas, all we need is a glowing splint, right? And that glowing splint will relight, or if the splint is already lit, it will begin to burn or to glow brighter. Note that oxygen gas is a colorless, odorless gas, right? And the reason why the glowing splint relights is because oxygen supports combustion, right? That's the reason. Once again, oxygen gas, if you want to test for the presence of oxygen gas, you simply use a glowing splint. The glowing splint will be relighted. Or if you have a splint that is already being burnt, the splint will burn brighter or glow brighter. Next up is hydrogen gas. For hydrogen gas, it's also a colorless, odorless gas, but if we put a glowing splint over the hydrogen gas, it will out the glowing splint and you will hear a pop, a pop sound. You're gonna hear the pop sound. Now the reaction is hydrogen plus oxygen reacts to give us steam, which is water, right? That's the reaction. And the reason why we hear the pop sound, or the reason why hydrogen gas outs the glowing splint, is because hydrogen reacts very explosive in air to form steam, right? That's why we get the popping sound, simply because hydrogen is very explosive in air to give us steam, forming water vapor, of course. The next one is carbon dioxide gas, which is also a colorless, odorless gas. Let's recall, if carbon dioxide gas is present, we simply place a carbon dioxide gas in lime water or slaked lime, which is calcium hydroxide, and a white precipitate of calcium carbonate is seen. Here's our reaction: calcium hydroxide plus carbon dioxide to give calcium carbonate plus water. Now on heating, if we were to heat this calcium carbonate, it would redissolve in the water along with the extra carbon dioxide to form calcium hydrogen carbonate, which is soluble in water. So it would no longer look white, it would just look soluble. Alright? So once again, to test for the presence of carbon dioxide gas, we use slaked lime, which will be converted to a white precipitate. Now if we want to test for the presence of hydrogen chloride gas, which is colorless with a sharp acid odor, we use ammonia. We use ammonia gas. Right, and when we react these together, so it's going to be ammonia plus HCl give us ammonium chloride, which is a white solid, or it can be a white gas, a white vapor. Right, once again, if we need to test for the presence of hydrogen chloride gas, we use ammonia, which will form ammonium chloride, which is a white solid or a white fume. If we need to test the presence of ammonia, which is a colorless pungent odor, it has a colorless pungent odor, we wouldn't see it, but it would have a very sharp pungent odor. It smells almost like urine even. Right, so what happens if you need to test for the presence of ammonia? It changes moist red litmus paper to blue, right? Because it's basic, it's alkaline, so it's going to change our moist litmus paper to blue. Notice that the litmus paper is moist, so for the reaction it's going to be ammonia plus water to give ammonium hydroxide, which is alkaline, right? And of course we're going to be, if we add hydrogen chloride to this ammonia, right, similar to before, if we had hydrogen chloride to this ammonia, we form ammonium chloride, which once again is a white solid. Right, now once again, if you need to test for the presence of ammonia gas, you use litmus paper, or you can use hydrogen chloride gas. With litmus paper, it changes to blue because of the formation of ammonium hydroxide, or with hydrogen chloride it changes to a white solid precipitate, or white fumes are being seen. If we need to test for the presence of NO2 gas, which is nitrogen dioxide gas, this is a brown gas with sharp irritating odor. Just recall, brown gas with a sharp irritating odor. Now for this one, it would change our moist litmus paper to red, right? Why? Because once again, it's moist water. If we react water with nitrogen dioxide, we're going to form two different acids, right? We're going to form HNO2 and HNO3, one being nitrous acid and one being nitric acid, right? So we're going to form two acids. Acids change litmus paper to red, hence the color of our litmus paper. Once again, nitrogen dioxide gas is a brown gas, and it will change our litmus paper, or moist litmus paper, to red due to the formation of two different acids, nitrous acid and nitric acid. Up next, we have chlorine gas. Just recall, chlorine gas is a yellow-green gas, and it has a sharp choking odor, you know, like bleach, for example. Yes, so that's how you would expect chlorine to smell. Now for chlorine gas, it changes blue litmus paper, moist blue litmus paper, red. Why? Because once again, you have your chlorine reacting with water to form hydrogen chloride, which you know that in water it could be hydrochloric acid, acidic, hence litmus paper has to change to red. Now this reaction of the chlorine with the water also forms chloric acid, very similar to bleach. It also forms chloric acid, which bleaches the litmus paper, and the litmus paper will further change to white. So the hydrogen chloride causes the litmus paper to change to red, but because of the formation of the chloric acid, it causes it to change to colorless. It's bleached out completely. Right? Just remember, chlorine gas is a yellow-green gas, and to test for the presence of chlorine gas, we use red litmus paper, which changes, we use blue litmus paper, which changes to red because of the presence of the water, which causes the formation of hydrochloric acid and chloric acid. Hydrochloric acid causes it to change to red, the chloric acid causes it to bleach out or to change to white or colorless thereabouts. Next we have SO₂ gas, which is sulfur dioxide gas, right? This gas is colorless and it has a pungent odor, colorless and pungent. To test for the presence of this gas, we use potassium permanganate, which would change from purple to colorless due to the reduction of the permanganate to Mn2+. Right? That's the reason why we're reducing our permanganate to Mn2+, hence it goes from purple to colorless. We can also use potassium dichromate, which changes from orange chromate ions to the Cr3+ ion, which is green. So these two tests can be used to test to see for the presence of our sulfur dioxide gas, where the sulfur dioxide gas would reduce both the potassium permanganate from purple to colorless and also reduce the potassium dichromate from orange to green. Note the ions that they are reduced to. Lastly, we have water vapor. Now water vapor, it is colorless of course and odorless, but to test for the presence of water vapor, we use two things. We can use anhydrous copper sulfate, or we can use dry cobalt 2 chloride. You might have heard of this one before. So it would change dry cobalt chloride paper from blue, so cobalt chloride paper is blue, it would change it from blue to pink, because once we add water vapor to the cobalt chloride, it becomes hydrated and we form the hydrated cobalt chloride, which is pink. So once again, water vapor changes cobalt chloride from the dry cobalt chloride paper from blue to pink. Next is that it changes anhydrous. Remember that anhydrous means without water. So anhydrous copper sulfate is actually white, but once we hydrate it, those crystals, they become blue. The same copper sulfate that you see in the lab is the same thing, but the anhydrous form is white, but once we add water vapor or water to the copper sulfate, it becomes blue, the hydrated form, which is hydrated copper sulfate. Okay, now let's see if we have learned anything. This question says, Joy carried out some tests on a solid labeled R. Some of her observations and inferences are recorded in table 1 below. Complete the table by filling in the other observations and inferences. So this says a sample of R was heated strongly in a dry test tube and a glowing splint was placed in the mouth of the tube. Note what we're using here. Brown fumes are seen. Brown fumes, of course, that has to be NO2 being present, that's our inference, and the glowing splint being relit, that means that O2 oxygen gas is present. Overall, this concludes the presence of our NO3 ions being present. It's just a simple recall. Recall that if it were potassium or sodium nitrate, we form one gas, which would be oxygen gas. You're going to see it be relit. But if it's any of the metals, calcium or any metals below that of calcium in the reactivity series, we get two gases. We get nitrogen dioxide and oxygen gas, where nitrogen dioxide is brown and oxygen gas, of course, is colorless, but it relights the glowing splint. These tests help us to identify the presence of our NO3 anion. It says aqueous sodium hydroxide was added to a solution of R until in excess. So we're adding aqueous NaOH, right, until in excess. A white precipitate is formed which dissolve in excess to form a colorless solution. right? So a white precipitate is formed with aqueous sodium hydroxide. Now if you recall that calcium, aluminum, lead and zinc, they all form white precipitate, right? They all form white precipitate when we add sodium hydroxide. But in excess, the only soluble ones, so all are insoluble except those of zinc, aluminum and lead, right? So all are insoluble except those of zinc, aluminum and lead. So this is our inference right here. The fact that we formed a white precipitate, it could have been either of these, but because it says that it was in excess, it dissolved forming a colorless solution, it has to be either zinc and zinc ions present, aluminum ions or lead ions being present. Here we go. All form insoluble precipitates except those of aluminum, lead and zinc, which form soluble colorless solution, and we use our acronym SAC to remember those for sodium hydroxide. So right now our R could be any of these, Z, A or P. Next we have aqueous ammonia was added to a solution of R until in excess. Aqueous ammonia, that's so NH4OH was added. A white precipitate was formed which dissolved in excess to form a colorless solution. Now the fact that we have a white precipitate, if you recall, for ammonia, in ammonium hydroxide, calcium does not form a precipitate. In ammonium hydroxide, they all form white precipitates except those of copper, iron, and iron 2+ and iron 3+. In excess ammonium hydroxide, they all are insoluble except those of zinc and copper, which are soluble, and the zinc would of course look colorless and the copper would look blue, so you'll see a blue solution. So let us go back and see what we have for our question. Next, aqueous ammonia was added to a solution of R until in excess a white precipitate formed, right, which dissolved in excess to form a colorless solution. So it says a white precipitate formed. Now when we have ammonium hydroxide, we do form white precipitates with a lot of the cations, but notice that this is in excess, and in excess it forms a colorless solution. The only cation that I can think of that would form, even before that would form a colorless solution, if you think about it, all of our cations are insoluble except those of zinc and copper, right? So if we say dissolved, only zinc and copper are soluble, but it says in excess it forms a colorless solution, and only zinc would form a colorless solution in ammonium hydroxide. Copper would have been a blue solution. So therefore zinc hydroxide would have been formed to show the presence of Zn2+ ions. The ionic equation is going to be Zn2+ plus OH minus to give Zn hydroxide, all being aqueous because once again it is soluble, so it has to be aqueous. Next we have a solution of R was made in dilute nitric acid and a few drops of silver nitrate solution were added, followed by aqueous ammonia. Now for this, chlorine ions are present, right? That's what it says, chlorine ions are present. Now if you recall, for when we react, we have 3 of our group 7 elements. We have chlorine, bromine and iodine. For chlorine, when we add our silver nitrate to chlorine, it forms a white precipitate. When we add silver nitrate to bromine, it forms a cream precipitate. When we add silver nitrate to iodine, it forms a yellow precipitate. Now if we were to further add aqueous ammonia, we realize that the chlorine that we formed, the silver chloride that we would have formed from the previous, that would have been soluble. Then the silver bromide would be partially soluble, so it would be like a slight cream, and then the silver iodide would be insoluble, so you would see an insoluble yellow precipitate at the top, right? Now note for this test is for chlorine ions, so of course it's going to be silver nitrate plus chlorine ions, right? We're going to write the ionic equation, it's going to be silver plus chloride to give us silver chloride. Now the observations that we would see, since this is chlorine, we're going to see some white precipitate on addition of the silver nitrate, and it is also going to be soluble in aqueous ammonia. So those two would be the observations that you would expect for this reaction here. I try to do this one as quickly as possible because I was actually recording. I thought I was recording, but it was not being recorded. So let us get into this one. Alright, so a few drops of dilute sodium hydroxide were added to a small portion of a solution A in a test tube. Green precipitate formed. Once you see green precipitate, whether it's ammonium hydroxide or sodium hydroxide, it has to be iron 2+ ions present. If it were red brown, it has to be iron 3+ ions present. Now it says the green precipitate darkened when left to stand and turned orange at the top of the test tube. So this, we're assuming that oxidation would have happened. We leave our iron 2+ to stand, or green iron 2+ to stand. It's being exposed to oxygen, so of course oxidation is going to happen. So the iron 2+ was oxidized to form iron 3+. That's why it changed to orange, or that's why it was darkened at the top. The next test, a few drops of dilute sodium hydroxide were added to small portions of solution A in a test tube. The test tube was heated gently, and a colorless gas evolved with a pungent odor. When I think pungent odor, I'm already thinking about ammonia. It also says that this gas turned damp red litmus paper to blue. The only gas I know is able to do that is ammonia gas because of its basic properties, or simply because it's alkaline. So I have here ammonia gas is present due to the pungent odor. Then we say that the litmus paper changes to blue as the ammonia is alkaline. It also says that a colorless solution is formed, right? Colorless solution is formed simply because our ammonium hydroxide, when we have our ammonium hydroxide and we further add more sodium hydroxide, this ammonium hydroxide is going to dissolve, which forms a soluble solution, right? It completely dissolves, so we won't see any colors. We're going to see a soluble solution. All right, so let us do a quick summary of reactions with aqueous sodium hydroxide. So all cations form a white precipitate except those of copper 2+, which is blue, iron 2+, which is green, and iron 3+, which is red. They are all insoluble in excess sodium hydroxide except those of ZAP, which is zinc 2+, aluminum 3+, and lead 2+, all forming a colorless solution in excess sodium hydroxide. The ammonium cation forms no precipitate but releases ammonia gas when it is warmed, and this ammonia gas is a pungent gas. For the reactions with aqueous ammonium hydroxide, no precipitate is seen with calcium 2+. In excess ammonium hydroxide, white precipitates of aluminum, lead, and zinc are seen, and all are insoluble in excess ammonium hydroxide except those of zinc and copper. But we would see a colorless solution of zinc hydroxide in excess ammonium hydroxide, and we would see a blue solution in ammonium hydroxide in the presence of copper 2+. Let's start the comparison between both the sodium hydroxide and ammonium hydroxide reactions. Aluminum, lead, and zinc dissolves in excess sodium hydroxide, but only zinc dissolves in excess ammonium hydroxide. Copper 2+ forms a blue precipitate in both sodium hydroxide and ammonium hydroxide, but it dissolves in excess ammonium hydroxide to give a deep blue solution. And of course, iron 2+ and iron 3+ are both, you can see colors in both when they react with sodium hydroxide and ammonium hydroxide, where iron 2+ is green and iron 3+ is red brown. For the effect of heating the solid, if carbonate anions are present, carbon dioxide gas is evolved, which changes lime water to milky, right? If nitrate anions are present, that is, if it's potassium or sodium nitrate, oxygen gas is evolved, which relights the glowing splint. However, if the metal is below that of calcium, or if the metal is calcium nitrate, then a brown gas is evolved. A brown gas of nitrogen dioxide is evolved, and oxygen gas relights the glowing splint. For the reaction with dilute nitric acid, carbonate also gives carbon dioxide with dilute nitric acid, which we know that we can test for carbon dioxide using calcium hydroxide, which gives a milky color in the presence of calcium hydroxide. Right now, if there is sulfite anions present, it gives sulfur dioxide gas, which turns acidified potassium permanganate from purple to colorless. Note that it also changes potassium dichromate from orange to green. For the next test is the reaction with concentrated sulfuric acid. If carbonate anions are present, carbon dioxide gas is released, which we can use calcium hydroxide to test for the presence of our carbon dioxide, and we would see a white precipitate. If our sulfite anions are present, sulfur dioxide gas is released. Once again, we see potassium permanganate change from purple to colorless. If chlorine is present, right, chlorine anions is present, we would see some white fumes when hydrogen chloride reacts with ammonia gas. That reaction, ammonia gas plus hydrogen chloride gives us ammonium chloride, which is a white fume or a white gas. If bromine anions are present, we would see a red-brown gas, and if iodine anions are present, we would see a gray-black solid, and a purple vapor would be seen upon heating of this solid where we're having the sublimation of iodine. For the reaction with silver nitrate and aqueous ammonia, note that initially with the silver nitrate and chlorine ions or the chloride anions, we would see a white precipitate, and it is soluble in aqueous ammonia. For bromine anions or bromide anions, we would see a cream precipitate, which is slightly soluble in aqueous ammonia. For iodide anions, we would see a pale yellow precipitate, which is insoluble in aqueous ammonia. For the reaction with barium nitrate and dilute acid, carbonate forms a white precipitate. Matter of fact, they all form a white precipitate. Carbonate, sulfite, and sulfate, they all form a white precipitate. However, if carbonate is present, right, and we add dilute acid, it would dissolve and we would form carbon dioxide gas. If our sulfite is present, it also dissolves, forming the SO₂ gas. For SO₂, you can use potassium permanganate to test for the presence of SO₂ gas. And if our sulfate is present and we add dilute nitric acid, it would remain insoluble, so we would not see a change per se. For the last test is all the gas test summary. Note that oxygen gas relights the glowing splint. Hydrogen gas, it pops the glowing splint. Carbon dioxide changes lime water to white. Hydrogen chloride gas, when we react it with ammonia, we see a white fume of ammonium chloride. For ammonia, ammonia changes red litmus paper to blue, and ammonia has a pungent smell. If it is Cl anions present, it changes blue litmus paper to red because of the presence of the hydrogen or the hydrochloric acid, which is formed on reaction with the water, the moist water on the litmus paper. And also this would also be bleach because we also form chloric acid, which is very strong and bleaches the litmus paper. So the litmus paper changes from blue to red, then to colorless or to white. Right, and for sulfur dioxide, we use acidified potassium permanganate, which changes from purple to colorless. If it is nitrogen dioxide is a brown gas, and if water is present, it changes cobalt chloride paper from blue to pink, and it also changes copper sulfate and hydrous copper sulfate from white to blue. Now this summarizes all that we would have done in this video. Thank you for watching Miss Wallace Teaches Chemistry. Bye.
Miss Wallace teaches chemistry, chemistry.